Okay, so I'll begin the session. Uh, yeah. Good evening, everyone. Welcome to the week 4 of NPTEL live session for discrete mathematics. In case there are okay, in case there are newer people here, okay, hi Akaksha. In case there are newer people here, then my name is Bhavya. So I'll be taking these live lessons Tuesday 6 p.m. Okay. Now, without further ado, the topic for this week is relations. Okay. This is quite an interesting aspect of discrete mathematics. And what we plan to do is relations are actually used to, as the name says, it's trying to relate two things. For example, we talk about, okay, A is greater than 3 is greater than 3 is greater than 2. Okay. And we say that, greater than represents a relation. Now take note that this is different from something like 3 plus 2. This is not a relation. This is an operation. Okay. And there is a totally different field of discrete mathematics that deals with these kind of objects, operations. So things like, algebra, group theory deals with this realm of mathematics. But here, okay, there is another rich field of discrete mathematics which proposes to study these kind of things. All right. And yeah, we are exactly planning to study these kind of things, okay, but in a more mathematically rigorous way. So what is a relation? Okay, a relation, I'll quickly do it. It won't be as intense as the lectures, but a relation R on a set is a subset of, on a set A is a subset of A cross A. Now what is A cross A? A cross A is what is called the Cartesian product. Okay. So what is the Cartesian product now? So if A is 1, comma 2, comma 3, there are three elements in this set. What is A cross A? Okay. You simply multiply with each of the elements here. I don't mean the arithmetic multiplication. I mean the following. So 1 with 1, club them together. So you got 1, comma 1. And then 1 with 2. Okay. So you got 1, comma 2. And then 1 with 3. Okay. Then 1 comma 3, and then do the same 2 comma 1, 2 comma 2, 2 comma 3, 2 comma 1, 2 comma 2, 2 comma 3. There are total 9 coordinates. Yeah, that's right. Good. And 3 comma 1, 3 comma 2, 3 comma 3. Okay. 3 comma 1, 3 comma 2, 3 comma 3. Okay. So this is what is called the cross product, okay, or the Cartesian product, okay, A cross A. Now, what are we saying R is? A relation R is simply a subset of the cross product. So, I can take, what is a subset? I can take any set of elements from here, and that is what I call a subset. So, for example, R, I can take, let's say I take 1 comma 1 from there. Okay, I take 1 comma 3. I take 2 comma 3, and let's say 3 comma 2. This is a relation on A, on the set A. Okay, now let me call this R1 and let me write R2 is 1 comma 1, 2 comma 3, 4 comma 3. The idea is that this is still a relation actually, but this is not a relation of the set A. Why? Why? Because, no, sorry, because this 4 does not belong to my set A. Remember that my set A consisted of 1, 2, 3. Okay, so 4 does not belong to my set A, and this is still a relation, but not on set A. Okay, I mean, this is as simple as it goes. Okay, this is what a relation is. You can just take the cross product of a set with itself and then take any set of subset of elements, and that's it. That you call it as a relation. Now, how do you represent these relations? Okay, one way to represent them is what is called the graphical form, or what is called graphs. Okay, there is an area called graph theory, okay, which is an entire vast area in computer science and mathematics in itself. And how do you represent as graphs is, okay, I also this these are what are called tuples, okay, tuples or tuples. So these are what are called tuples, okay, and I can read it as 1 comma 3. I can read it as 1 is related to 3. This is how I can read it as, or I can write a, yeah, 1 is related to 3. That is how I can, the other way of seeing it. So if one, so what I do, so how do I make the graphical form? How do I represent this relations? Okay, we already saw the set theoretic form. Okay, that is this way. Write it as tuples. How do I do it? I just make what are called vertices or nodes, okay, for all the elements in A. Okay, here I think A is 1 2 3. A is 1 2 3. So I make nodes, okay, I make vertices. And if 1 is related to 3, I draw an edge with an arrow as follows. 1 is related to 3. And next, 2 is related to 1. 2 is related to 1. 2 is related to 3 as follows. And 2 is related to 2. How do I show that? Well, intuitively, what you just do is, I just make an arrow that goes back to 2. 2 is related to itself. This is what is called the graphical relationship, graphical form. This is another, so this is one way to represent relations. The other way to represent relations would be as follows: matrix form. In a similar light, what we do is I label all the rows with elements in A. Again, A is 1, 2, 3. Now what do? I use 0 or 1 to show the membership. Okay. So the question I ask is 1 related to 1? So no, in this relation at least, I'll write a 0. Is 1 related to 2? No. Is 1 related to 3? Yes. Good. Then I'll write a 1. Similarly, is 2 related to 1? Yes. Is 2 related to 2? Yes. 2 related to 3? No. And is finally 3 related to 1? No. 3 related to 2? No. 3 related to 3? No. So this is another way to show it. Matrix form. Okay. I hope everything is fine until now. Okay. Albert says yes. I hope Akanksha and Gomati are also fine so far. Okay. Okay. So yeah. So the question. Okay. We'll solve the first question. Okay. Represent the following relations. Okay. On the set 1 2 3 4 in the graphical form and matrix form. We just saw how to do it. Okay. And the set is 1 2 3 4 this time. Okay. Let me solve E. Okay. So let me solve the graphical form for A. Okay. So what did I say? The set is 1 2 3 4. So I make vertices for each of them. Okay. Next, what I do is I look at each of them. Okay. 2 is related to 2. Means that I make an arrow from 2 to 2. 2 is related to 3 means I make an arrow from 2 to 3. 2 is related to 4 means I make an arrow from 2 to 4. 3 is related to 2. I make an arrow from 3 to 2. 3 is related to 3, meaning I make a self loop. Okay, these are what are called self loops. And 3 is related to 4, meaning I do this. So this is my graph. And similarly, matrix also, I mean, um, 1, 2, 3, 4, 1, 2, 3, 4. Okay, we label, okay, the rows and columns. Okay, so firstly, 2 is related to 2. Oh, sorry. See, 2 is related to 2. Okay, so I make a 1 here. Next, 2 is related to 3. 2 comma 3 position, I put a 1. Next, um, 2 is related to 4. So 2 comma 4 relation position, I put a 1. 3 is related to 2. 3 is related to 2. So here I put a 1. And 3 is related to 3. Here I put a 1. Then finally 3 is related to 4. I put a 1. Oh, I put a 1. And the remaining places I put zeros. So this is the matrix form. Okay. Now I guess yeah. Okay. So part I hope everyone is fine so far. The second part B is actually even simpler. Okay, because you just have 1 1 2 2 3 3 3 4. So the graphs becomes quite interesting in this case. 1 2 3 4. Okay. Okay, I make a vertex, each vertex for each element in set A. Now what do? There is a relation from 1 to 1, from 2 to 2, okay, 1 to 1, 2 to 2, 3 to 3, and 4 to 4. And can you describe to me what the matrix would look like in this case? So for this relation given in B, what would the matrix look like? Yes, Kumati, Akanksha. Good, yeah. Yeah, the matrix would be a diagonal matrix. In other words, the diagonal elements are 1. So this already gives, okay, I'll draw it anyway. 1, 2, 3, 4. 1, 2, 3, 4. Okay. 1 is related to 1. So 1 comma 1 position, okay, 1 comma 1 position, I put a 1 here. So 1 is not related to anything else. 1, 2, 1, 3, 1, 4 are not there. So 1, 2, 1, 3, 1, 4, I put zeros up here. Okay. Similarly, 2 comma 1 is not there. 2 comma 2 position, I put a 1. Okay, because it is there. Okay. Then 2 comma 3 is not there. 2 comma 4 is not there. And similarly, I do this. And 3 comma 3 is there. 3 comma 4 is not there. 3 comma 1, 3 comma 2, 3 comma 4, sorry, 4 comma 1, 4 comma 2, 4 comma 3 is not there. If you see, only 4 comma 4 is there. So you see that the matrix is a diagonal matrix, and we also infer from here that the diagonal elements actually capture the self loops. When one element is related to itself, that is actually captured by the diagonal positions in the matrix. Okay, good. So I hope everything is fine. I hope Albert, is everything fine? Okay. Okay. Albert, can you? Okay. Okay, moving on. The question is as follows. Consider a relation R, A comma A comma B, B comma C, C comma B, C comma D, D comma A, D comma B. Okay. Which of the following graphs represent the relation R? Can you guys try your hand out at it? So there are 4 graphs given. The relation R is given, and you need to check which of these graphs actually capture the relation R. Albert says C. Okay. Let's see. Okay. Akanksha, Gomati, can you try? Okay, Akanksha says C. Okay. Okay, let's see. So let's look at the first one. A comma A is related to A. Okay. Next, A comma B, A is going to B, good. B comma C, B goes to C, good. C comma B, C goes to B, right. C comma D, here is the problem. C should be going to D, it's not the other way around. So this one is not my answer. Okay. Let's try the next one. A comma A. Here itself we have a problem because A does not have a self loop. A is not related to itself. There should have been a self loop here. So this is wrong. Oh, okay. Gomati also does C. Yeah. And yeah, let's see. Okay. Yeah. So let's look at this one. A is related to A. Good. A is related to B. Good. B is related to C. Yes. C is related to B. Yes. C is, oh sorry, yeah, C is related to D. Let's see. Yes. D is related to A. Yes. D is related to B. Good. Yeah, then yeah, you guys are correct. The answer is C. What is wrong with D? A goes to, there's a D goes to A, D goes to C. Yeah, I think, yeah, what is wrong with the D part? This D goes to C, this is wrong. There is no such line from D goes to C, edge from D goes to C. Okay, good. So yeah, these are some simple questions, okay? And now we'll study the type of relations that are there. So yeah, I won't go in depth as in the lectures, but just to jog your memory, I'll tell you what the types of relations were in the lectures. So we can categorize relations into different types, okay, and they may be more than one type at the same time. So firstly, what we have is called the reflexive relation. Okay, so what is a reflexive relation? Relation is reflexive if it contains all possible a comma a for all values of a in a. What does it mean? Like if my relation is on the set 1, 2, 3, let's say, okay. If okay, or here itself I can say, if my relation is on the set 1, 2, 3, 4, then my relation should necessarily contain, where is it? Yeah, my relation should necessarily contain 1, 1, okay, should contain 1, 1, 2, 2, 3, 3, and 4, 4. This is what is called reflexive. These elements should be there. So let's look at relation R1. Okay, is it reflexive? That is the question. 1, 1 is there. Is 2, 2 there? Yes. Is 3, 3 there? Yes. 4, 4 there? Yes. So this relation R1 is reflexive on A because all 1, 1, 2, 2, 3, 3, 4, 4 are there. Okay, and yeah, here R2. Okay, here 1, 1 is there, 2, 2 is there, 4, 4 is there, but 3, 3 is not there. So other than AA can also come. Yeah, you can. Yeah, Albert. For example, here you see that 1, 2 is there extra. So that is not a problem for us. Okay. As long as it contains 1, 1, 2, 2, 3, 3, 4, 4, it is fine. Else what you would have is you'd only have one possible reflexive relation for every set A, and that would be like this set. Right? Yeah, okay. So yes, yeah, the question is, yeah, the answer is yes. You can have other tuples along with these, reflexive tuples. 1, 1, 2, 2, 3, 3, 4, 4. So can anyone tell me now, what would the matrix look like for a reflexive relation? I mean, just a peculiar property of a matrix. Yeah, diagonal, Akanksha, Albert. Yeah, right. So we saw before that the diagonal elements actually represent the relationship. Yeah, diagonal matrix. That's right, Gomati. The relationship the relationship that an element has it with itself. Okay, if the diagonal elements are all ones, it means all the elements are related to itself. So other than diagonal, there could be ones and zeros and so on. But a peculiar property about reflexive relations is the diagonal elements will always have ones. So you can try it offline also. Okay, you can try, let's say, plotting this one. Okay, this R1 will have diagonal as all ones, and this one will not have diagonal as all ones. Okay, good. Now symmetric relation. Okay, a relation R is symmetric if whenever AB is in R, it is true that BA is also in R. Again, let's look at it by example. What it simply means is if something like 1, 2 is there in the relation, then it must be true that 2, 1 is also there in the relation. Okay, simply flipping the two elements, simply flipping them, okay, and then check whether it's there in the relation. If that is the case, then our relation is what is called symmetric relation. Okay, and yeah, okay. So let's look at it. 1, 1. So is it symmetric? That is what we want to check. R1. Okay. So yeah, 1, 1 flipping 1, 1 will again give 1, 1, and it is obviously in the relation. 2, 2 flipping 2, 2 it will again give me 2, 2, 2, comma 2, and it's there in the relation. 1, comma 2, 1, comma 2. Flipping it, I get 2, comma 1. Is 2, comma 1 in the relation? Yes, 2, comma 1 is there in the relation. So far it is symmetric. If I flip 2, comma 1, I get 1, comma 2. So this is also fine. Next, 3, comma 4. When I flip 3, comma 4, what do I get? 4, comma 3. And yes, I do get 4, comma 3. And when I have 3, comma 3, flipping it will give it itself. So this is a reflexive relation. This is a symmetric relation. Okay. Next, yeah, Albert says R2 is not symmetric. Yeah. Why is it, Albert? Why is it not symmetric? 3, 4. Yeah. In R2, yeah, 3, 4 is not present. Good. So in R2, you have this element 4, 3. But if this relation were to be symmetric, then flipping it, that is 3, 4, should be present. 3, 4 is not present, but it is not present. So this is not symmetric. Yeah, good. So I hope others are also fine so far. Let's move on. Antisymmetric. Now this doesn't need much of an introduction because antisymmetric simply means like it is opposite of that of symmetric. Okay, that is, it is antisymmetric if whenever AB is in R, it is true that BA is not in R. Okay, and but it does not does Yeah, but this is okay. So far it's good. Yeah, so this is what is meant by antisymmetric. Okay. Transitivity. Okay. But I'm not giving an example for antisymmetric because this R2 that I showed earlier, okay, is good enough for antisymmetric because 4 3 is present and 3 4 is not present, so it satisfies. Okay. Sorry. R2 is not antisymmetric because this 2 3 and 3 2 they are present there, so it's not purely antisymmetric. So R2 is not an example. Yeah. So finally, okay, the final thing before moving on to the problems is transitivity. A relation R is said to be transitive if whenever AB is in R, BC is in R, okay, it is true that AC is in R. Okay. If whenever AB is in R, BC is in R, then it is true that AC is in R. So you should look for these kind of forms. A related to B, B related to C, then A is related to C. This is called the transitivity property. Okay. Again, let's check. A is 1, 2, 3, 4. We want to check whether R1 is reflexive or not. So here let's look at it. Sorry, transitive or not. So 1 is related to 1. Do we have okay, this is A is related to B. Do we have B is related to C? That is 1 is related to something? No. So yeah, we cannot move on from here. We cannot test the property on this 1 comma 1 anymore. Okay. So 2 comma 1. Okay, it again ends with 1. We need now 1 comma something, but that is also not. Oh, there is 1 comma 1. So 2 comma 1, 1 comma 1. Then transitivity property says that 2 comma 1 should be there. Yeah, 2 comma 1 is there. Right. So it is fine so far. Next, 2 comma 3, 3 comma 4. 2 comma 3, 3 comma 4. Then 2 comma 4 should exist here. 2 comma 4 exists. So fine so far. Next, 3 comma 4 and 4 comma something is not present, so we don't care. 2 comma 2 and 2 comma something. 2 comma 2 and 2 comma 3 are there. So do we have 2 comma 3? Yes. 2 comma 2 and 2 comma 1 is there. Do we have 2 comma 1? Yes. Finally, 2 comma 4 and 4 comma something is there. So no. And everything is satisfying this property that whenever A, B, comma B, C is there in the relation, then it is transitive. Okay, then this is transitive. Yeah, Albert says C. Are you talking about the question below this? Okay, we will come to that. So R. Okay. Yes, below is not visible. Oh, okay. Yeah. I'll finish up with this. Is R2 transitive? That is the question. 1 is related to 1. 1 comma something is not there. 2 comma 1, 1 comma 1 is there. See, 2 comma 3, 3 comma 4 is there. So this is in the AB BC form. It is in the AB BC form. This would mean that 2 comma 4 should have been there in the relation. Okay. Okay, and 2 comma 4 is there in the relation. So this is fine so far. Now let's look at 3 4 4 1. Okay. Let's look at 3 4 4 1. This would mean that 4 comma 3 comma 1 should be there in the relation. 3 comma 1 should be there in the relation, but that is not the case. So this is not transitive. Okay. So now that we've done the recap, let us try this question. I think Albert was talking about this question. Okay. So yeah, I'll zoom in. Consider the relation R on the set 1, 2, 3, 4 described by the following matrix. This is the matrix. The relation is reflexive but not symmetric, symmetric but not reflexive, reflexive and symmetric, neither reflexive nor symmetric. Okay, I think Albert has said it's C. Sir, I was answering this one. Oh, okay. Albert has said C. Okay, Albert. Let's see the others also try. Akash also says C. Okay, you have this matrix. Okay. Yeah, option C is correct. It is reflexive and symmetric. Now, what is one way to see it? One way you can do it is you can break it down into 1, 2, 3, 4, 1, 2, 3, 4, and then make this relation. Kumati is saying 1, 4 is not there. 1, 4 is not there. 4, 1 is also not there. Yeah, that is true, Kumati. 1, 4 is not there, but I don't see where the problem is. Do you mean in symmetric it's a problem? Okay. Yes, sir. So symmetric it should be a problem, you are saying. 1, 4 is not there, but anyway 4, 1 was not there in the first place. So it should not create a problem from what I can see. Okay, I'll solve it once, okay? Let's see. Okay, yeah, okay, go. R equals, okay, 1, 1, then 1, 2, then what do we have? 2, 1, 2, 2, then 2, 4, okay, this one is 2, 4, then here is 3, 3, this is 3, 3, 3, 3, look at all the places where it has ones, and this is 4, 2, and finally this is 4, 4. Now the first question, is it reflexive? To check whether it is reflexive or not, all a comma a, okay, in my set should be there. From my set should be there. In other words, 1, 1, 2, 2, 3, 3, and 4, 4 should be there. Let's see. 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is there. So immediately R is reflexive. Next, what do you do? You check whether it's symmetric. Okay. So flipping 1, 2, I get 2, 1. Right. So 2, 1 is there. So 2, 1 is there. So fine so far. And next, flipping 2, 4, I get 4, 2. So 4, 2 is there. The remaining elements 1, 1 or 2, 2, if I flip, I'll get it itself. So it will obviously be there in the relation. Okay. So yeah, flipping each of the tuples, I get that it is still a member of the relation. So therefore R is symmetric. And the relation R is reflexive and symmetric. So the answer is C. Good. Okay, is it fine? Yeah, Gomati, when you are saying 1, 4 was not there, 4, 1 was not there to begin with. So I don't need 1, 4 to be there for the relation to be symmetric. Okay. If, for example, if I had a 4, 1, if this was 1, then yes. then yes, I needed another one to be here. And yeah, okay, good. But also to say this, there is a shorter way to look at this also. Okay, reflexive. I've told you already the way to check reflexive if you know if the diagonal elements are all ones, it's immediately reflexive. How do I know if the relation R is symmetric? R is symmetric if matrix is symmetric. You may have heard about symmetric matrix in your high school. A symmetric matrix is simply when you flip the rows to columns and columns to rows in the matrix, right? I get the same thing. So that is what is called a symmetric matrix. So columns and rows match. So for example, the first column, for example, first column says 1100. The first row also says 1100. Second column says 1101. The second row says 1101. Then the second column also says 1101, and so on. So just by looking at the matrix itself, I can actually tell whether it's reflexive or symmetric. So this is actually a faster technique. But like if you want to look at things like transitivity and so on, it may not be very structurally simple to observe that. Okay. Good. So yeah, let's try this. Okay, set of interesting questions. Determine whether the relation R on the set of all people. Okay, this is my set. Okay, all people is reflexive, symmetric, antisymmetric, and or transitive. Okay. So I'll do the first few, but if time permits, we might do the others also. So A. Let's look at A. Okay. So it's saying R is AB such that A is taller than B. Now the question is it reflexive? So let's see. Is A comma A in R for all A in people? For all people. What does this mean? A comma A is in R. A is taller than A, or A is taller than itself. So can you be taller than yourself? I mean, logically no, right? Otherwise there is a contradiction. So you are not taller than yourself. So this is not true for any. So there is no person who is taller than itself. So such kind of people will not exist in my relation. So it is not reflexive. Okay. Now let's look at symmetric. So what is symmetric? It means that if A comma B belongs to R, then B comma A belongs to R. Okay. Albert says antisymmetric. Let's see. Okay, let's see, Albert. If A comma B is in R, it means A taller than B. But if it were the case that B comma A were in R, then this would be B is taller than A. Right. So it cannot be that A is taller than B and B is taller than A at the same time. Assuming that taller does not mean same height, at least same height. Taller means strictly a greater height. Okay. Then it is not symmetric. It is not symmetric. So is it antisymmetric then? It means if A comma B is in R, then B comma A is necessarily not in R. And yes, Albert, the answer is yes. Okay. Because if A is taller than B, it is necessarily true that B is not taller than A. So yes, it is antisymmetric. Finally, transitivity. Okay, what does transitivity say? Okay, what does transitivity say? Transitivity says that if A comma B is in R, and B comma A is also in R. Sorry, B comma C is in R. Okay, A comma B is in R. B comma, there is no third person. No, I mean, Albert. Let's assume that the set is set of all people, right? So the set is much larger than 2. Then you have enough people, and then A comma C belongs to R. So what is the logic here? The logical statement here is A is taller than B, B is taller than C, then A is taller than C. So yeah, you can imagine it yourself. Like if there is a tall person who's taller A, okay, who's taller than B, who's slightly shorter, and there's a much shorter person who's called C, and A is taller than B and B is taller than C, then obviously A is taller than C, right? And this means transitive is true. This statement is true. A is taller than B, B is taller than C, then A is taller than C. Yeah, Albert. Okay. So yeah, so the final answer is that it is antisymmetric and transitive. So I would like you guys to try this one, B. Okay, A and B were born on the same day. Okay, A is related to B if A and B were born on the same day. Is the relation reflexive, symmetric, antisymmetric, transitive? It could be a combination. Okay, please try the question B. Okay, Akanksha is already reflexive, symmetric, transitive. Okay, Albert says reflexive. Okay, good. Let's wait for a few moments. Okay, so let's look at the first case, reflexive. Okay, so reflexive, again, A is related to itself. So is it true that A comma A for all A and A? Okay, is it true that A is related to A? A is obviously born on the same day. A and A born on same day. Okay, my birthday comes on my birthday. So this is truly true. So it is reflexive. Next, symmetric. Okay, A comma B is in R. Okay, Gomati, reflexive, symmetric, transitive. Yeah, good, Gomati. A comma B is in R means that A, B share the birthday. Okay, and B comma A, is it true that B comma A is in R? Is it true that B comma A share birthday? Yes. Gomati says not antisymmetric. Okay, let's check that, Gomati. Antisymmetric. So antisymmetric says A comma B in R, then B comma A not in R. So like A, B share birthday, but how can it be that B, A don't share birthday? Unless B doesn't want to treat A or something. So yeah, this is clearly not true. Okay, this is logically false. So it's not antisymmetric. Next, transitive. And here I can directly say that if A, B, P, C share birthday among themselves, A, B share their birthday, B, C share birthday, then obviously A, C also share birthday. So yeah, good guys. This is reflexive, symmetric, and transitive, and it is not antisymmetric. Yes. Okay. Would you like to try C? C says R equals AB. A has the same first name. Okay, I think, and this is same first name as B. A has the same first name as B. Akanksha says reflexive, symmetric, transitive. So again, it's reflexive, symmetric, transitive. Okay. Oh, okay. Albert has only replied R, S, and T. Okay. Um, let's see. The question is, A has the same first name as B. So, okay, reflexive. Firstly, we can just directly see that if A has this, A always obviously has the first name as himself. Like Akanksha as her first name as Akanksha, Gomati as her first name as Gomati, and so on. So it is reflexive, obviously. Symmetric. If A has the same name, first name as B, okay, then B also has the same first name as A. So it is symmetric also. Good. Antisymmetric. This would obviously be false because if A is if A shares the same first name as B, then it is not true that B should not share the same first name as A, right? And transitive. If there are three people, and A shares the first name same as first name as B, B shares the same first name as C, then obviously A shares the same first name as C. So it is transitive. Okay, good. So yeah, now we've got a few ideas on this. So yeah, let us do a slightly more tougher one. Okay, slightly more. Let us try this one, or maybe I'll give you a few minutes to think about it. So the question says, let R be a relation on the set of ordered pairs of positive integers. Okay, this is my set, ordered pair of positive integers. So take note that it is positive. Okay, such that PQ comma RS. Okay, so this is my tuple now. PQ is related to RS. Okay, PQ is related to RS such that P minus S equals Q minus R. So PQ is related to RS whenever P minus S is equal to Q minus R. Which of the following is true about R? R is reflexive, symmetric, reflexive but not symmetric, not reflexive but symmetric, neither reflexive nor symmetric. Okay. Think about this one. The key thing here is that the set is a set of ordered pairs. Okay. So the set looks something like ordered pair of positive integers, something like Albert Webster. Do we need to arrange the relation? No, not necessarily. What do you mean by arrange? Do you mean like, do I need to arrange the tuples in some order? P plus R equals Q plus S. Okay, yeah, I mean, this is allowed. P plus R equals Q plus S. Since these are positive integers, these are allowed. That is allowed. Yeah. So yeah, you are allowed to rearrange these because yeah, this is um, this is arithmetic. So yeah, I was saying that ordered pair of integers look something like positive integers, something like 1, 1, 2, and so on, 2, 1, 2, 2. So what would a relation on A look like? It would look something like, P minus S equals Q minus R. So 1 minus 2 minus. Okay, conscious is A. Let us see. Okay, so let's see. Yeah, like I said, A is a set of ordered pairs. Okay, and what does R on A look like? It should be a subset, okay, of A cross A, which means it should be a subset of tuples containing tuples containing tuples. So that's why it is of this form: P comma Q, R comma S, and so on. So now, what does the question say? Which of the following is true? Okay, so now R, okay, some P comma Q, R comma S, belongs to R if P minus S equals Q minus R. This is what they say. Now, first let us check for reflexivity. Okay, if it were reflexive, then A comma A should belong to R for all A. This is what we are asking. But what is RA? RA is an ordered tuple. So this can be P comma Q, and this is another P comma Q. Is such a tuple in R? That is what we are asking. Okay, P comma Q, is it related to P comma Q? Furthermore, now how do we check? Let us check. If P comma Q were in R, if P comma Q comma P comma Q is in R, then okay, so this is if not, then what will happen? Then P minus S equals Q minus R. Where is S? S is here. P minus this outer one is equal to Q minus this inner one. Right? So P minus Q is equal to Q minus P. But then what do you have? These are positive integers. So the other, since these are positive integers, so this is P minus Q. since these are positive integers, okay, like subtracting them, okay, would create a minus sign, but negating them would change the sign. Okay, so p comma q is clearly not equal to minus p comma q. This is a contradiction. Yeah, Albert, it is not reflexive. That's right, because p minus q is we are getting p minus q equals minus p minus q, and these are positive integers. This can never happen. Okay, thus R is not reflexive. Okay, so yeah, we've reduced the answers. Next, it is asking to check for symmetricity. Now let us check that. Okay, when is it symmetric? P comma q, q comma p. Okay, or actually no. A comma b is there in R, then b comma a is in R for all ab. Is it true? This is what we are asking. So take an a comma b, p comma q, and some r comma s. So p comma q is my a and r comma s is my b. Okay. Then if it is an r, then what do we mean? Then we have that p minus s equals q minus r by definition. Right. Now let's do the other way around. Okay, this is true. Okay, let's check if b comma is there. B comma is r comma s comma p comma q is an r. If it were in r, okay, if this were to be in r, then p minus r minus q, the outer ones, equals s minus p. Okay, now let me take the minus common, or minus of q minus r equals minus of p minus s. I cancel out these and we get and we get that p minus s equals q minus r, which is true from here. From this, we know that this is true, and therefore when we flip that and checked whether it satisfies the property, it is true. Therefore, this belongs to the relation. Thus, r comma s, p comma s, p comma q belong to the relation, and therefore is symmetric. So it is not reflexive and symmetric. The answer is C. Let's see what you guys answered. Okay. Yeah, right, Albert. It's C. Okay. Okay. Akanksha had answer A. Yeah. Akanksha A says both reflexive and symmetric. The problem is in reflexive. Okay. It is not reflexive because if it were to be reflexive, then we get this contradiction. The important fact, note that we could do this because these were positive integers. And if it was not necessarily positive integers, then 0 could have been there. It creates, minus of 0 is 0 and strange kind of contradictions. Okay. So, yeah, the answer is C. Okay, good. Um, okay, what is left? Okay, yeah. So the final question on checking reflexive, symmetric, and so on. Okay. Uh, so this concept of subtracting the endpoints of tuples be valid for every relation. So this concept of subtracting the endpoint of tuples be valid for every relation. Uh, no, Albert. I mean, this is not valid for each relation. It's only valid because our relation was defined that way. Our relation said that PQ and RS are related if P minus S equals Q minus R. So all the relations need not satisfy this. But can you do, if you are asking, can you do subtraction between the values within the tuples? Yes, you can. There is nothing stopping you to do so. But you should make sure that you can actually perform subtraction. That they are either integers or natural numbers. Objects where you subtraction is actually well defined. Okay, but yeah, okay, good. So, yeah, final question on checking reflexivity, symmetricity, and so on. Okay, determine whether the relation R on the set R is reflexive, symmetric, antisymmetric, and/or transitive when xy is in R, if and only if x plus y equals 0. Okay, I'll do the first one. Okay. So this is like R is containing all tuples such that x plus y is equal to 0. Okay, and let's say x y. Let's say A, the set A is the set of real numbers. Okay, it's not mentioned here, so I'm just assuming it to be the set of real numbers. So yeah, let's try this. Is it reflexive? That is the question. Well, reflexive would mean that all x comma x and r belong to 0, belong to R. But that is clearly not true, right? Yeah, Albert. Yeah, it's not reflexive because it's clearly not true. Why? Because 1 comma minus 1 is a counter example. Since 1 is not equal to minus 1. Symmetric, let's see. Symmetric says if x plus y is equal to 0, does y plus x equal 0? Yes. So it is symmetric. Okay. Now transitive. What is it asking? Antisymmetric also. Antisym. Obviously this is not antisymmetric because it's saying if x plus y is 0, is it true that x plus y, flip it, okay, y plus x is not equal to 0. This is obviously false, so it is not antisymmetric. Finally, transitive. I mean, I'm going faster because we've seen several examples like these ones. So transitive, x plus y equals 0, y plus z equals 0, then is it true that x plus z equals 0? Okay, let's see. X equals minus y, now y equals minus z. Now we want to check what x plus z is. X plus z is nothing but minus y from here and plus z. And what is what is minus y equal to? Minus y is equal to minus of minus z which is equal to plus z. Okay. Yeah, which is equal to minus or minus y, which is equal to plus z, which is equal to y plus z. Oh, what? Okay, sorry. This should be z, which is equal to z plus z, which is equal to 2z. So this is not necessarily true. So it is not transitive. Okay. Let me verify it once again. X equals minus y, so I put minus y here, and y equals minus z, so minus or minus z is z, which is 2z. So x plus z. Oh, okay, sorry. So then what you get? X plus z equals 2z. So yeah, x plus z equals 2z. So I mean, it's not necessary for this to be equal to 0. Z should be 0. For this to be 0, z should be 0. But that is not always the case, because z can be anything from real numbers. So this is not necessarily true, not necessarily transitive. So yeah, I hope it was clear here. Okay, I went slightly faster. Okay, but let me know if there was a problem. But yeah, I would like to ask you guys to try this one. Xy is greater than or equal to 0. Xy is greater than or equal to 0. Okay. Um, I mean, the full relation is, x comma y is in R if and only if xy is greater than x times y is greater than. Symmetric and transitive. Let's see. Okay. So symmetric definitely. So antisymmetric is out of the box, and reflexive. Reflexive. No. And oh, it should be reflexive also, right? But transitive, yeah, I think so. X times y is greater than 0. Yeah, Gomati says reflexive symmetric transitive. Yeah, I think I agree. I think it should be reflexive also. Let's see. Um, R equals xy such that x times y is greater than or equal to 0. So yeah, reflexive. Is it true that x times x is always greater than 0 for all x? This should be true because either x is positive or negative. Okay, either x is positive x is negative or x is 0. So if it is positive, then what do you have? X times x square, okay, and it is positive, and multiplication of positive numbers is always positive, so this is greater than 0. If x is negative, okay, so let's say x equals minus a, where a is positive. A is positive, so you can represent a negative number this way, and x square is nothing but minus a times minus a, which is equal to plus a square, which is clearly positive and greater than or equal to 0. And if x is finally 0, then you have that x square is equal to 0 times 0, which is equal to 0. Okay, so yes, it is reflexive. Yeah, okay, is it clear, Albert? Yeah, okay. Albert, yeah. So next is symmetric. Now here it is clearly symmetric. We can see it because x times y is greater than or equal to 0. Then obviously y times x will be greater than or equal to 0, right? Because multiplication, it does not matter which order I multiply with, and this is always true. So antisymmetric is out of the equation because it is symmetric. Transitive, x times y is greater than or equal to 0, y times z is greater than or equal to 0. Okay, then is it true that x times z is greater than or equal to 0? That is the question we want to ask. Okay, 1 minute. Okay, so x times y is greater than or equal to 0, y times z is greater than or equal to 0, then is it true that x times z is greater than 0? Well, what are the combinations that are possible? For it to be greater than or equal to 0, either both are positive or both are negatives. Okay, either both are positive. So for example, here this is positive, this is positive, and this is negative, this is negative. So let's say this case, take this case when x is positive, y is positive, y is positive, y is negative, z is negative. Okay, positive, negative, negative. Then x times z equals positive times negative, which is negative, which is less than 0. So yeah, the answer is that no, this is not transitive. Okay, is this clear? Albert, Akanksha, Gomati, and the, I cannot pronounce this name, the Jor. Sir, y is same in both x related to y and y is related to z. That is true. Oh, right. Good catch. Yeah. Yeah, good catch, Akanksha. So it cannot be that y is negative and here it is positive. So if this is the case, then this should necessarily be positive, and z should therefore also be positive to create greater than or equal to 0. Good. And if it were negative here, then y should necessarily be negative, and z therefore should be necessarily negative to create greater than or equal to 0. And yeah, sorry. Good. Then it should be that x times z is, you know, positive times positive or negative times negative, which is positive. So it is transitive. Really sorry. Okay, good catch. Um, yeah. So having said and done that, uh, okay, the remaining ones. Okay, this should be x y. Okay, the remaining ones I would implore you to try it offline. Okay, I'll upload the notes. Okay. Uh, Here, let us move on to some other questions. Okay. So the question says the following. Okay. How many symmetric relations are possible on a set of cardinality 12? So you can either arrive at this logically, but if you see the lectures, there is a formula to do so. How many symmetric relations are possible on the set of cardinality 12? Okay. 2 power 156, 2 power 155, power 78, 2 power 77. We have to find the number of symmetric relations. Okay, no answer so far. Okay, Akash says C. C is 2 power 78. Albert also says C. Okay. Yeah, let's try. So, 2 power 156, 155, and so on. So, yeah, if we use the formula directly, yeah, and that is the simplest way to go about it. No, the formula for number of symmetric relation on set A, you might have seen it in the lectures, is 2 power n square plus, or not, okay, a size of a square plus size of a divided by 2. I think this is correct. Yeah, Albert. Or, yeah, which is 2 power n times n plus 1 divided by 2. Correct. So, if there was a way to arrive at this. There was a way to arrive at this, by looking at the corresponding matrix, counting the ones below the diagonal and, you know, and then, choosing the ones in the diagonal and so on. And finally, you'll arrive at this formula. Okay, I won't show it because it's already there in the lectures. But if you want to clarification, then please let me know. So anyway, this is the formula. So now the application is straightforward. Okay. So what is size of A? Size of A is nothing but 12. So number of symmetric relations equals 2 power 12 square plus 12 divided by 2, which is 2 power 144 plus 12 divided by 2, which is equal to 2 power 156 by 2, which is 2 power 2 sevens are 14, 1 2 8 16, 2 power 78 is the answer. That is C. So yeah, good. It's C. Yeah. So yeah, now we are nearing the end of the. There are just how many? About 2 or 3 many questions left. Okay. Now we are nearing the end of the session. So I just want to talk about equivalence classes and partitions quickly. So a partition, okay, is a collection of subsets that are disjoint and covering. Now what does this mean? Disjoint means that the subsets don't overlap with each other. They don't share anything with each other. And what does covering mean? Covering means that when you take a union across all the subsets, it will give you the superset itself. In other words, if this is a partition of subsets, A1, A2, and so on, AN, where each AI is a subset of this A, this mother set A, okay, then firstly it says covering. It covers A, which means that if you take union across them, then it will give you exactly A. And if you intersect any two of them, then you get a disjoint. This is what is called disjointness. There is no, they don't share any elements together. So, for example, if this is the set A, then partitions will look like this. Okay, they don't overlap, but they cover all the elements in. For example, A is 1, 2, 3, 4, 5, 6, 7, 8. Pi 1, okay, is 1, 2, 3, 4, 5, 6, 7, 8. So the question is this a partition? Firstly, take union across all 1, 2, 3, 4, 5, 6, 7, 8. Then do you get the original set? Yes, I get the original set. 1, 2, 3, 4, 5, 6, 7, 8. Next, do they share elements among each other? No, they do not share any elements among themselves. So since they don't share, it is a partition. Okay, yeah, good. So this is a partition. Now if I have pi 2 equals 1, 2, 4, 5, 6, 7, 8. Now is this a partition? That's the question. Well, they are disjoint, that is, they do not share elements together, but if you see here, 3 is missing. Element called 3 is missing from here, right? So this is not covering. So the covering condition is not getting satisfied. So therefore it is not a partition. So, but if 3 were to be here in this, let's say, then again it becomes a partition. Okay. Good then. Now, what is an equivalence relation? An equivalence relation, so can we take it as 3? Yeah, that is also allowed. So let's say, yeah, Albert says like, if can I take it as this? Yeah, this is a perfectly good example. This is a partition because it is covering. If you take the union, then you get 1, 2, 3, 4, 5, 6, 7, 8. And if you take the what do you call? If you look at the intersection, they do not share any elements with each other. So it is perfectly fine. Yeah. Okay, Albert. Okay. So equivalence relation. Okay. So remember this as RST. An equivalence relation is a special type of relation. Okay, if a relation is said to have these properties that are reflexive, symmetric, transitive, then you know our relation is said to be an equivalence relation. For example, this A divides B. Every element divides itself, so it is reflexive. If A divides B, oh, okay, sorry, it is not. It's not A divides B actually. It should be B leaves same remainder. Okay, AB leaves same remainder when divided by say 4, okay, or 3. So if A leaves the same remainder when divided by 3 as B, let's say A also leaves 1, B also leaves 1, then it is also true that B and A is also the relation, they leave the same remainder. And transitive is like if A leaves the same remainder as B and B leaves the same remainder as C, then obviously A and B leave the same remainder when divided by 3. Now, why are equivalence relations interesting? You may have seen it in the lectures. Okay, equivalence relations are interesting because they are as good as partitions, mind you, because they partition a set A into smaller partitions. That's what it does. For example, this remainder thing that I told you. Okay, and for example, this remainder thing I told you, you should see it. Okay, you can see it offline. It partitions the set into leaves those sets that remainder 0, those that leave remainder 1, and those elements that leave remainder 2 when divided by 3, and it exactly partitions them. You should have seen it in the lectures, but I'll be moving on there. So after that quick recap, let's see. Okay. The question is, which of the following collections of subsets are partitions of 1, 2, 3, 4, 5, 6? Okay. Yeah, so can you quickly answer this question? This is fairly straightforward. Okay, that was quick. Okay, let's see. 6, 3, 5. क्या कनेक्शन से C. Okay, others, Gomati. Yeah, okay. Let's see. Here already in A, okay. 1, 2, 2, 3, 4, 4, 5, 6. Here there is already a problem because these are not distinct. So A is not the answer because they are sharing elements. The overlap should not happen between partitions. 1, 2, 3, 6, 4, 5, 6. Let's see. Okay, they are disjoint. But do they cover? No. 4, okay. 1, 2, 3, 4, 5, 6. Okay, so they are not disjoint actually because 6 and 6 is already shared. So, yeah. Covering is out of question. No. So, C. 2, 4, 6, 1, 3, 5. They are disjoint. Yes, they are disjoint. If we take the intersection, we don't see any sharing. They don't share any elements. Next, is it covering? When I union them, it would give me 1, 2, 3, 4, 5, 6. Yes, and they are covering. So the answer is C. Good. What is wrong with the last one? The last one, it has 1, 2, 4, 5, 6, but it does not have 3. No 3. So it is not covering. Okay, good. So please explain the remainder and equivalence. Oh, okay, I'll do that. Yeah, okay, Albert. See, let's see how the partitions are getting formed in the case of remainder. Okay. So this is my relation R. Okay. This is my relation R. Now what is R saying? A is related to B if A and B leave the same remainder when divided by 3. Okay, this is my relation. Good. Now, so question I ask you is, okay, let's say A is equal to natural numbers, okay, including 0. Okay. So what remainder, what is, 0 related to in R? This is the question I ask you. Okay, so 0 should give me the same remainder whenever it is divided by I mean anything related to 0 should give me the same remainder when 3 is divided by 0. So what is 0 divided by 3? 0 mod 3, that is 0's remainder on divided by 3 is 0. Okay, so what leaves the remainder 0? All the multiples of 3. So that is 0, 3, 6, 9, and so on, 12, and so on. Correct? Yeah, 0. Now what is 1 related to in R? Now 1 mod 3 is 1, and what is it related to? So it leaves whatever it's leaving the same remainder with. So 1, 4, 7, 10, 13, and so on. When divided by 3, they leave the same remainder. So if you observe, it's not just that 0 is related to these elements. These elements are only related to elements within themselves. Like 6 is related to 3, 9 is related to 6, 9 is related to 12, 9 is related to every element in this set. Similarly, 10 is related to every element in this set. And finally, what is 2 related to in R? So let me see. 2 mod 3 equals 2. So it's 2. Okay, and 5, 8. Yeah, Albert, and so on. 8 and 11 and so on. Now all the elements, and if you observe, like I said before, any element in this set is only related to elements in this set, not from elements from this set, neither from elements from this set. So what we realize is, this relation, equivalence relation, actually forms a partition. Why? Because let me call this P1, P0, P1, P2. If you observe P1, P0, P1, P2 are partitions. They never share elements with each other. And when you union them, you will get all the natural numbers. Or rather, when you union them, you will get all the relation. All the natural numbers. So are you getting it? So, and therefore they form these clusters inside. If you look at the set of natural numbers, let us look at this be the set of natural numbers, then it forms these clusters where these are the ones which leave remainder 0, remainder 1, remainder 2. And these are only related with each other. partitions on the remainder basis. That's right. On the basis of remainders. So in some kind of basis, they'll leave a remainder, and usually it will be directly related to the somehow it will be directly related to the equivalence relation. Therefore, we say what is the use of equivalence relation? It is used to partition sets into um, these smaller partitions, disjoint partition. Okay. Um, yeah. So I hope that was a good enough introduction for this. Okay, Albert. So still, I mean, if you have further questions, please let me know. Yeah. So we just have two questions left now. Okay. So this is slightly, it's not very challenging also, but still. So please look at this question. Okay. Consider the relation R such that A is related to B if and only if A plus B is even. Which of the following is true about R? R is not an equivalence relation. R is an equivalence relation with one equivalence class. Okay. Oh, sorry. I forgot to tell you. And these partitions, okay, that it forms are what are called equivalence classes. Sorry. The partitions that get formed are called equivalence classes. Okay. I think it is done. I think it's called equivalence set in the lectures. Okay. So R is an equivalence relation with two equivalence classes. R is an equivalence relation with three equivalence classes. So is it an equivalence relation? If it is an equivalence relation, how many um, equivalence classes does it form? Or in other words, how many partitions does it induce? Um, so firstly, let's check whether this is an equivalence class or not, equivalence relation or not. Okay. So let's say A, B is in R. Okay. Oh, sorry. Okay. For it to be an equivalence relation, it should be reflexive, symmetric, transitive. Let's check. So let's check the first property, reflexive. Is AA in R for all A? Now we know that it is in the relation only if A plus B is even. In our case, B is A, so A plus A equals 2A, which is always even. So yes, A comma A belongs to the relation. Next, symmetric. If A comma B is in R, then is it true that B comma A is in R? So A comma B is in R means that A plus B is even. Then obviously it is B plus A is also even. Yeah, symmetric. So yeah, it is symmetric. Symmetric is true. Reflexive is true. Finally, transitivity. Let's see. A comma B is in R. B comma C is in R. Then A comma C is in R. That is the question. A plus B is even. B plus C is okay. Albert, equivalence. Okay, so it is an equivalence class. You see, Akanksha says C is the answer. C is two equivalence classes. Okay, let's see Akanksha. A plus B is even. B plus C is even. Right. Then is A plus C also even? It should be even because when do you get um, a sum to be even? Either both are odd or both are even. And if this was odd, then even this would be odd. because B is odd and C would also be odd to create an even. And if it were even, this would be even. Then A plus C would be odd plus odd, which is even. And A plus C in the even case would be even plus even, which is equal to even. So yeah, it is transitive also. So it is equivalence relation because RST properties all are satisfied. Now, yeah, so after says C equivalence relation with two equivalence classes. Okay, so let's see. Okay, if we want to find the equivalence classes, always look at what is mathematically called closure. Okay, where the elements cannot escape from the partitions. Okay, like for example, the elements here could not escape; they were only related to each other here, and these were only related to each other here. So let us look for that kind of a property. So yeah, actually we already looked at the. So okay, let's say A and B are related to each other. Okay, and or rather let's look at like before. Okay, the question I ask is what elements are A related to, or let's make it more simpler. What elements is 2 related to? Now 2 would be related to 2. Okay, everything adding to 2 would be even. So that would make even. So if I add 3, it would not make it even. It would make it 5. So if I add 4 to 2, it would make it even. If I add 5 to 2, then 5 plus 2 is 7. It would not make it even. But if I add 6 to 2, it would make it even. And similarly, 8, and this side I can put 0 also, and 10 and so on. And then you realize, oh, okay, it's not just the elements 2 is related to, it's the element 6 is related to, 8 is related to, and so on. So we realize that, all these are all even elements. So pick any other element from outside, okay, from outside this set, and let's look at its equivalence class. So R1 related to. So 1 is related to itself. 1 plus 1 is, even. Is 1 related to 2? No. 1 plus 2 is not even, it's odd. Then 3 is 1 plus 3 is 4, it's even, good. So then we realize, oh, okay, if I add 5, 7, 9, 11, and so on. And then again you realize, oh, okay, if I just pick any number, you realize that whatever it's related to with is, is inside the set itself. So for example, 7 plus 5. 7 plus 5 is odd, even. So these are all odd elements. Am I done? So this is similar to Fibonacci series. In a way that, yeah, in a way it is similar because, we are having cumulative sums. Yeah, that's right. So you are doing 4 plus 2 is 6. But in Fibonacci, remember that, we are relating with the previous element. So 4 plus 2 is 6. Oh, okay, you are doing that. Yeah, 4 plus 2 is 6. So 6 plus 4 should be 10 and so on in Fibonacci. But I agree that it is true to the point that, every time we are adding 2 and 2. This is somewhat different in the way, yeah, but in the sense that, the previous element we keep adding in Fibonacci. So, only valid for finite digits. Only valid for finite digits. I do not understand. But anyway, Albert, any number that does not have a finite number digit is not a natural number actually. Okay. So all elements, all odd elements, and this covers the entire natural number. So this is nothing but the even number. This is nothing but the odd number. So even union odd is equal to natural number. So it covers And finally, they are disjoint. Even intersection odd is not is equal to 5. So yeah, I think Akanksha had said that there are two equivalence classes. Yes, there are two equivalence classes. 2EQ class. Answer is C. Okay, we have few we have very little time left. Okay. Yeah, okay, but I think Albert, this is fine, right? The answer is C. There are two equivalence classes, those with odd elements and those with even elements. So yeah, I think this one will take time, so I will not be doing this one. Okay, but you can take a screenshot of this question. You can take a screenshot of this question, and you can try it offline. Okay, or but as I told you before, I'll also be uploading the notes, okay, in the drive. So this question will be there. Okay, so think about this question. Okay, it's not very difficult also, and I think in a previous question I had not solved the other parts. Okay then, I think these are all. I hope. Okay, but please let me know if you have any more questions. But besides that, we have come to the end of the session. Again, like before, the next session will be happening on Tuesday 6 p.m. again. Yeah. Okay, Albert. Good. Okay, Akanksha. Okay, so see you on Tuesday. Okay. Have a good week. So Gmeet is more fine. Oh, okay. Yeah. Gmeet is good, but I think it does not handle too many than Teams. Oh, is it so? Yeah, Gmeet is more portable in that sense. Plus, you don't need to install any additional software, right? You can just log in from the browser. If you're doing it from the PC, that is. Okay then. Good night. Can you continue? Oh, can we continue follow-up classes here? Yeah, yeah. I mean, see, Albert. We can either. Wait, I'll stop the recording.